Welcome back to Differential Equations. In this video, I want to look at phase portraits in two dimensions. A lot of the concepts here tie very closely back to ideas we talked about for first-order ordinary differential equations. So before we get too far into this, I want to review a couple of those concepts. First of all, remember that we studied an autonomous differential equation. An autonomous ODE was something in the form y prime equals some function of y, where there's a first order derivative, no higher order derivatives, and the change depends only on the dependent variable y, not on the independent variable, which we generally assume to be t. And then we graphed what we called the phase line, where we just set up a single y-axis and started trying to determine what was going to be happening with that. One of the first examples we looked at when we were studying autonomous ODEs was a population model. Specifically, we started with the naive approach, which is the exponential growth model, which says that y prime is equal to some rate of growth that we called k multiplied by the population. The more population there is, the faster the growth occurs. The less population there is, the less growth can occur. But then we wanted to modify that slightly, and we did that by multiplying an extra term here that took a form something like 1 minus y over n, where we said that n was the carrying capacity, the maximum size that the population in the area could attain. So that as you go close and closer to the carrying capacity of the population, then this fraction, or this new thing in parentheses, goes towards 0. If there's no more food for more of the animal to live, you can't grow anymore. But if you have a very small population, then the stuff in parentheses is basically 1 and it didn't change anything. And so we analyzed this in our phase line by looking for our equilibrium points, which we got by setting that derivative equal to 0. And in this case, we get that y equals 0 or y equals n. We plotted those things on our phase line, and we tracked whether y would be increasing or decreasing in various regimes. If y is smaller than 0, then this first term here becomes negative, which means that the population is decreasing. If y is between 0 and n, everything is positive, which means that the population is increasing. And when y is bigger than n, this thing becomes negative, which causes the population to decrease again. We could then classify those equilibrium points as a stable node, where the population wants to be there. If it's higher, it will decrease. If it's lower, it will increase. And an unstable node, where the population really doesn't want to be there. If the population is 0, it's not going anywhere. But if the population is bigger than 2, it's going to start increasing, right? And it will increase until it hits that carrying capacity. So if it is at 0, you can't get population out of nothing. If it is bigger than 0, it will start growing. All of those concepts translate incredibly nicely into systems of equations. An autonomous dynamical system is any differential equation which can be written in the form x prime equals some f of x and y prime equals some g of x and y. And just like with the ODE version, notice here that there is no t dependence in either of these. And one of the simplest examples to understand is once again going to be a population dynamics. This time, let's look at a predator-prey model. So we have two populations that we are monitoring. X is going to be the population of some prey species, possibly rabbits is the common one. And then Y is going to be some predator species, and foxes is the common thing used here. If the foxes were not there, the rabbits would continue to grow and the growth would be in a logistic map. But the more foxes there are, the more they are going to hunt the rabbits, which will decrease the population. The fewer rabbits there are, the lower the carrying capacity for the foxes. So you get this interesting feedback cycle that shows up. So we're again going to have some constant k. The rate of growth is going to depend on the number of members of the species present. And actually, let's rewrite this a little bit. It'll be a little bit easier to put my constant in here. Again, instead of the carrying capacity just being based on the number of rabbits, there is some relationship between the number of rabbits and the number of foxes. The more foxes there are, the smaller the carrying capacity. The fewer foxes there are, the greater the carrying capacity. So we get something that looks kind of like this. The growth rate of foxes, again, going to depend on what we have going on. But here it's going to be the opposite order. The more rabbits there are, the greater the carrying capacity is, and the easier it is for the foxes to reproduce, or to feed themselves even. So we want some c times x to be a positive term. But then there is some other aspect involved. The more foxes there are, the easier it is for foxes to reproduce. Fewer foxes there are, the harder it is. So we'll have something like cx minus d in here. All right, I don't know what these constants a, b, c, and d are. I am not an ecologist, so I don't even care what these constants are. Let's just make our lives really easy and set them all equal to 1. That really makes things easy on ourselves. And now from there, we want to do the same sort of thing we were doing before. So let me take this and bring it onto a new page so that that page break doesn't get in my way. And since we have two populations that we are studying, I guess we need two coordinate axes, the two-dimensional coordinate plane. I'm focusing on the first quadrant here because it is complete nonsense to have the population be negative? Right? What would it mean to have a negative number of foxes in the region? I have no idea. But we can start off with a couple of rather simple examples to look at. What if we had an initial condition on the x-axis? Initially, there are rabbits, there are no foxes. Well, the way I've set this model up, the dependency of the carrying capacity is entirely based on the number of foxes. So without any foxes, well, then we have x prime equals x, because y is equal to 0, and y prime equals 0, because y is equal to 0. So from here, we're going to see growth that just continues in the x direction. If there were no foxes, the rabbits would, well, breed like rabbits. They would continue to grow in population, and our model didn't give any other reason to cause them to stop growing. We assume that the field is large enough that our study will end before we've reached the point where the rabbits have run out of vegetation to eat. But what about something over here on the y-axis? Well, if we set if we are on the y-axis, that means we're setting x equal to 0. So there are no rabbits to begin with. And if there are no rabbits to begin with, well, we have 0 times 1 minus y, which is going to be 0. The rabbits aren't going to change in population. If there are no rabbits, there will not suddenly become rabbits. But then in the y change, y prime equals y times 0 minus 1, which is negative 1. And since y is a positive number, we assume that the populations are always positive. That means that over here, the populations will continue to shrink. And they'll continue to shrink until we get to the point 0, 0. I guess I shouldn't have drawn that one in blue. Let's go back to white, I guess. And here we end up in a slightly different situation that we didn't really see in the one-dimensional case. If we are on the y-axis coming down towards the origin 0, 0, this is a stable point. We will reach it and stop. If we are on the x-axis and we are very close to the point 0, 0, this is an unstable point. We're going to grow and go away from this as fast as possible. So this forms what is known as a semi-stable node. What if we were somewhere else, though? What if we were somewhere up here within the xy space? So we have x somewhere between 0 and 1. We have y somewhere between 0 and 1. And, well, then that becomes interesting. As I've sketched this, I'm kind of assuming that y is bigger than x. But again, both of them somewhere between 0 and 1. So then x prime, we've got 1 minus y, which is going to be a positive number. So x prime is positive. We're going to grow in the x direction. And then y prime. We've got y, which is a positive number, but then we've got x minus 1. Since I said that x is smaller than 1, that means that x minus 1 is negative. So y prime is going to be less than 0. We're going to be growing in the x direction and shrinking in the y direction, which is something like that. But what if we were actually bigger than 1? And I guess I should mention, why did I think 1? Well, because 1 is an interesting value here. I just realized that I never wrote this down, but let's backtrack a little bit. If x prime is 0, that means that either x is 0 or y is 1. If y prime is 0, that means that either y is 0 or x is 1. Right? And we need both x prime and y prime to be 0 in order to have an equilibrium point. So the only real options are 0, 0, and 1, 1. So we've seen that 0, 0 was this semi-stable node. I guess 1, 1 is the other interesting point. Let's go ahead and just name this 1, 1. And let's see what is happening in various regions around it. I've looked kind of below 1, 1, where x is between 0 and 1, y is between 0 and 1. But if we continue on this path that we set up here, probably eventually we'll come over here somewhere where x is bigger than 1 and y is between 0 and 1. But what will happen at that point? If x is bigger than 1 and y is between 0 and 1, then my x is positive, my 1 minus y is positive, my y is positive, and my x minus 1 is positive. So I get that x prime is bigger than 0, y prime is bigger than 0. And now we're going to start growing in this direction. X and y are both going to change in a positive way, and then maybe we'll end up over here somewhere. And over here somewhere is a place where x is bigger than 1 and y is bigger than 1. Now, as soon as y becomes bigger than 1, notice that this term becomes negative. Everything else is still positive. So I get that x prime is negative, y prime is positive. Right? So y is still going to be increasing, so we'll be going kind of in this direction where x is decreasing. And doing that will get us over here somewhere, and now we'll be in the place where y is bigger than 1, but x suddenly is somewhere between 0 and 1. Right, and what happens there? If y is bigger than 1, well then this term is still negative. If x is between 0 and 1, then this term is back to being negative again. And we get that x prime is negative, and y prime is also negative. And for both of these things to be negative, that means we're going to have some change going in this direction. And I've kind of drawn this to make it look like a nice smooth circle. It certainly didn't have to be a smooth circle, but you get this pattern where things are going to oscillate a little bit. This construction of two-dimensional space is called the phase plane. It makes a lot of sense when we're talking about everything in terms of x and y that we're going to graph things in the xy plane. But in a lot of applications, well, the more typical variables that ecologists use would be r as the population of rabbits and f as the population of foxes, and the RF plane is not something you ever think about. So to emphasize that we're graphing these things that aren't spatial coordinates, calling it something like a phase plane is worthwhile. We could try to be more precise graphing this thing by hand, but I'm not going to because computers exist and they can do the work for us. All right, so here is a web-based piece of software called the Phase Plane Plotter. Let me scroll down to the bottom here so I can show the copyright statement real quick. All right, so the URL is here. That'll be posted in the description. Ariel Barton is the person who put the web version of it together. And if I scroll back up to the top, we can start plugging some things in. One of the things that you have to be careful of, as you can kind of see in the one that's already given there, is that multiplication is not assumed. You have to type it in explicitly. So if I want x times 1 minus y, I have to explicitly put that asterisk for times. And then I want y times x minus 1. The other thing that I want to point out here is I'm actually refilming a video that I've had before because they've updated this website. Over here, these checkboxes for variable length arrow, show time as color, show initial position, I find that those make it a little bit harder to see what's going on. So I find it's easiest to uncheck all of those things. I'll then point out that we can change the coordinates, the dimensions shown. And since we already established that we're going to be mostly in the first quadrant, then it will probably be useful to talk about this from something like -1 to maybe something like 3. 3 seems good, right? And then likewise for y, from -1 to 3. Just to zoom in a little bit, we know that our equilibrium points are 0, 0, and 1, 1. Those are the things that we're going to care about. Let's hit the graph phase plane button, and then let me scroll down so that we can see what's going on. A lot of the information here is kind of nonsense. Again, I've drawn it just so that we can very clearly see what's happening on the axis. But down here, this is where there's a negative number of foxes. Over here is where there's a negative number of rabbits. Those are nonsensical, they cannot happen, so we don't really have to be concerned about it, but we should understand it. And then we've got all these arrows showing where the population, or how the population is moving. And you can see that they're starting to form these loops. I can make that a little bit more clear. If I have an initial condition, I can click on the graph and it will start following the path. So from here, we've gone downward, we've looped around way out here, looped around way up there, and continued on. If I click in a couple of more places, it will give me a couple of more curves, and we get this circular pattern, which is sometimes referred to as a limit cycle. The model that we've chosen here, the one that we have used for this, gives us these constant patterns where the population of the rabbits is going to grow and shrink, the population of the foxes is going to grow and shrink, and it's going to follow this pattern as a, starting here, we have a relatively small number of rabbits, so we can't feed the fox population, so the fox population plummets. Now there's very few foxes, so the rabbits have plenty of room to grow. Now there's plenty of rabbits, so the foxes can eat, and the foxes eat and, well, decimate the rabbit population, and it just continues. And if we know the population of rabbits and foxes at any one time, we can put that information in here. If we knew a little bit more about the dynamics of the system, we might have better variables. Or remember, our constants, we set all 4 of them equal to 1, just so that we could draw something. And I said that that would give us numbers that have nothing to do with actual populations, but it gives us a nice picture, and that's what I was after. All right, so that's the basic idea. I hit the wrong button. There we go. Back to the notes. And we'll wrap up with one more for you to take a look at. X prime equals 2x minus 3 halves y. Y prime equals cosine of x. I want you to use the phase plane graphing software In order to take a look at the phase plane for this dynamical system, just pick a couple of points at random to get some curves on there so that you can start exploring the initial conditions. Play around a little bit more with the settings if you so desire, but just familiarize yourself with that software for now. With that, I'll wrap up. Thanks as always for joining me. I'll see you next time.